Greetings and welcome, friends. Mr. Waddy here today. I'm going to show you a new technique to an old problem that we already technically have a great means of solving. And today we're going to solve linear equations by graphing. So we're going to kind of force an equation into a graphing situation and then find our solutions that way. And for the problems we look at today, our other methods are already going to be way better. But what they're doing in showing you this technique is they're introducing it with problems that you already understand. And this type of method could be used to solve problems that are much more complicated, that are beyond our current skill set. So it's still good to know how to do this, and so that's my pitch for it. But here you go. This is the idea. You can use a system of linear equations to solve a single equation with variables on both sides. So if I was solving this equation over here, all right, they've got all sorts of crazy letters in the place of numbers. What you could do is write two linear equations out of it. I could say, well, let's take this and write an equation y equals that. And let's take this and write an equation of y equals that. And the solution of when these are equal will occur when these two graphs equal each other. All right, so that's kind of the idea. Now, technically, we already know how to solve equations with variables on both sides. We bring the little guy to the big guy whenever possible. But if we were solving equations that were not linear, all right, not linear, we could actually use this same technique and solve problems that we don't currently know how to. So what they're saying is you write those two lines from this one equation by pulling both sides apart, and then you graph the system of linear equations, and the x value, underline that, of the solution of the system is the solution to the equation. That tells you what value of x would have made those equations true. So that's the idea. That's the idea. Let's see. Let me actually get set up my. Here we go. Here we go. I'm just going to use my print screen feature. It's so much faster. Even though it like dims the screen for you guys for a second, maybe that dimming will subliminally become like a, something you anticipate, like, ooh, what's coming next? Mr. Waddy is copying and pasting something. And I don't know, maybe not. So here it says, solve by graphing and check your solution. Now, we, like I said, already know how to solve this algebraically. I would have added x to both sides, and then added 5 to both sides, and then divided both sides. But it is possible to solve by graphing. So let's write two separate equations. I'll write y equals negative x. Maybe I shouldn't use green. I'll use green later. I'll write in purple and blue. So y equals negative x plus 1 would be one of the equations, right? Where I take this side and set it equal to y, a new variable that didn't exist until I just made it. And we have y equals 2x minus 5. So I've taken this side and written my own equation. And so if I want to graph these, let's find their slope and y-intercept. These already are in slope-intercept form. Slope is negative 1 here, right? Over here, the slope is 2. And over here, the y-intercept is positive 1. And here, the y-intercept is negative 5. Right? So let's graph these. Why not? Let's see. And I'm going to graph them quickly, assuming you've already seen my videos on graphing using slope-intercept form and rise over run and y equals mx plus b and all that, right? Blah, blah, blah. So let's see. Y-intercept is at 1. So here we go. There's my y-intercept for this purple line. And the slope is negative 1. So I'm going to go down 1 and over 1. And down 1 and over 1. And down 1 and over 1. And I kind of pre-selected a grid for us that was going to conveniently work out. Although sometimes you don't always know which quadrant your solution is going to end up. And so here is my line, my purple line. Purple line. Do, do, do. All right, let's check out the sky blue line. Y equals 2x minus 5, so the y-intercept is at -5, so 1, 2, 3, 4, 5, like so. Yeah, grab a ruler, good idea. You could, I think graphing using slope and intercept, you can, but I think making the table actually requires a whole lot of calculation sometimes. I mean, we've definitely learned how to do that, but using slope-intercept form is kind of using patterns to find, notice how quickly I was able to find multiple points here. Let's see, so if the slope is 2 from here, I'd go up 2 and over 1, and up 2 and over 1, and up 2 and over 1, right? So I'm able to generate a series of points, which would be the same ones I would have gotten from a table by doing that. Let's see, so, and I draw that line, like so. And so the intersection between these lines appears to be the point right here. And what is that intersection? What is the ordered pair? Oh, close, right? We read the x first. The x positive direction is over here, so that's over 2. And then, yeah, and then down 1, so 2, -1, right? Because for the y-axis, the positive y-axis was up. All right, so 2, -1 is the intersection of those lines, but then they told us moments ago that the solution of my system is the x value. All right, the x coordinate of the intersection will be our solution. So x equals 2, we are claiming, is the solution of the original equation. All right, and now they asked us to do a check, so let's just do a check. Is negative parentheses 2 plus 1 equal to 2 times 2 minus 5? So I'm plugging in this 2 for x to do a check everywhere I see an x. And so let's see, the opposite of 2 is -2 plus 1. Is that the same as 2 times 2, which is 4, minus 5? -2 plus 1 is -1. Is that equal to 4 minus 5, which is -1? Yes, it is. So it checks out. Hooray! Hooray. So we found a solution. All right, found a solution. Not the fastest way to find the solution in this case. Like I said, let me just show you how we would have done it algebraically. You don't have to write this down. I would have moved the little guy to the big guy, right? Bringing my x's together. And 1 equals 3x minus 5. I would have added 5 to both sides. Right, and this requires no graphing. Graphing, right, takes a lot longer, I think. 6 equals 3x, and then I would have divided both sides by 3. And I would have gotten the same exact answer. All right, I end up getting x equals 2. Right, flip it around, x equals 2. All right, so same answer. In this case, with lines, solving algebraically is much faster, but there will be ways, situations like if I suddenly gave you like a 2x squared and like a -x cubed, you might be like, I don't know how to solve that. And you guys don't. You technically won't know how to solve an equation like that until Algebra 2 or maybe pre-calculus. But if I was able to make a table of values, like Brandon was saying, for both of those, after I made those as 2 lines, I could have graphed both of those. They wouldn't have been lines. They would have been crazy curves. But the idea of finding their intersection still would have worked. And those are functions. They're just not lines, is what ends up happening. So let's see. Let's do another problem. I think, let's see. Did I give you guys... let's see. Did I give you guys problem 2 from the monitoring progress, or did I give you guys both? Let's do just 2 for sake of time. Although that other one does have a 1/2, but it's just slope, so it's not actually that hard to deal with. Okay, so here we go. Let's see if we can move through this one quicker and recognize how to do this. So first thing I'm going to do is set both of these sides, write them as their own equation. So I'm going to have y equals, and instead of negative 4x plus, or sorry, negative 4 plus 9x, I'm going to write that as y equals 9x minus 4, because I just like slope-intercept form. And then let's see, then the other line will be y equals negative 3x plus 2. The slopes for these, m will equal the 9. And here the m will equal, as a weird m, I started to write a b, and that's the problem, the negative 3. Right. And then our y-intercepts, I would have had b equals negative 4. And over here, b equals 2. Right? So let's graph these. So start or begin at the b, negative 4. So down 4, 1, 2, 3, 4. Plot a point. And move by the slope. Wow, this is a steep line. Up 9. So up 1, 2, 3, 4, 5, 6, 7, 8, 9. And over 1. Wow, I hope these lines intersect at one of those points. Oh dear. Oh dear. No, the y-intercept is whatever this number is. The x-coordinate of that y-intercept is 0. Let's see, I'm hoping these lines intersect somewhere close, otherwise I might need to redraw my grid. So let's see, to graph the second line. Oh yeah, they will. They will. I'm cheating. I'm looking at the answer here now. Y-intercept is at 2, so I start up at 2 here. All right, right there. And the slope is negative 3, so I'm going to go down 3 and over 1. And down 3 and over 1. Right, and I also could have technically gone up 3 and backwards 1 if I wanted. Let's draw that line. Oh, I gotta get my points further away from each other for my little ruler tool. All right, so here's my two lines. I have an intersection right here. Now, this is where graphing is a little bit weak because it's not the most accurate. But what do you think that point appears to be? What's the x-coordinate? It looks like it went over how far? Now, this is the 1. Yeah, it looks like it might have gone over a half. And it looks like it might have gone up a half. All right? So that appears to be the solution. And the one that I pick is just the x-coordinate. So I'm thinking that x equals 0.5 is the solution. All right? And that does, in fact, check out. I won't take the time to do it, but I'll show it to you. I'll just show you the book's answer. Bam, right there. Look at that check. If they plug in 0.5 for both of those x's, 9 times 0.5 is 4.5, negative 3 times 0.5 is negative 1.5, and everything cancels out. You get 0.5 equals 0.5. So it does work out in this case, and not too shabby. All right. Yeah. Yep, I'm a fan of just the old solving with algebra, but graphing does work. Now here's an interesting problem. I'm going to actually show you this a couple ways. We're actually going to have to graph this twice, I think. Yeah. Let's see. Let me grab another copy of this grid. Did I give you guys 2 grids or 1? Oh. For example, 2? Oh, flip the page, 1 more. Huh. All right, I gave you guys just 1. Well, you still can make it work. There's a couple ways we can do this. I'm going to show you the book's way first. All right, this one's going to actually have a whole bunch of different cases showing up. All right, so first, notice what do these things mean? You guys remember what those are? Those are absolute value, and absolute value tells me the distance something is from 0. Or if it's the absolute value of a positive number, it'll just give you that positive number because that number is distance is positive. But if we take the absolute value of a negative number, it will turn that negative number positive. So let's see. So absolute value. We even graphed absolute value functions back in the day. You might not remember how to do that. But if I write y equals absolute value of x plus 1 as my first equation, and y equals the... Oh, wait, actually, they broke this up separately. Oh, dear. Yeah, I so wasn't thinking of doing it this way. All right, I've got to undo what I just did. My bad, friends. My bad. I hope you don't run out of space. Well, you do have, like, the space on the next examples if you need to, because we won't be doing both of them. Okay, here we go. So absolute value, you guys might remember, I'm just going to do a quick little recall here. If I had the absolute value of x plus 2 equals 3, do you guys remember how we used to like split that into two separate equations, and I'd say either x plus 2 was equal 3 or x plus 2 was equal to negative 3. You guys remember that? All right, this is a kind of prerequisite skill to this. So I'm going to break this up into two cases, except the problem is I've got double absolute value. Okay? So either x plus 1 is equal to 2x minus 4, or x plus 1 is equal to negative of 2x minus 4. Those are my two situations here. Okay, it's the same idea as this. It's just weird that we're applying it to absolute values. And this actually does apply and take care of the fact that these are both absolute valued, and it wasn't just one side that was absolute valued. So I've actually got two separate cases here. Let's see. And I'm going to write multiple equations for this. So this one I'm going to either have y equals x plus 1 or y equals 2x minus 4. I'm going to graph both of these lines and find their intersection, and that will result in one of my solutions that makes this true. Over here, well, let's actually simplify this side. If I distribute that, I'd have x plus 1 equals negative 2x, and the opposite of negative 4 is plus 4. And let's write two equations there. I'll write these in different colors as well. So this one would be y equals x plus 1, right, if I just take this side. And this side, I would have y equals negative 2x minus 4. I was going to use two different colors, and then I just kept using green. So y equals negative 2x minus 4. So let's graph these. All right. The y-intercept of this is 1. And the slope was 1. So I'm going to go up 1 over 1. Up 1 over 1. Up 1 over 1. Etc. And so let's draw that line. And zoop, like so. Voila. And let's graph the second one. So this has a y-intercept at negative 4. Oh dear, 1, 2, 3. I didn't give us enough space. That's terribly unfortunate. Wow, all my pre-planning has failed us. And a slope of 2, so up 2 over 1. 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 It looks like I found the intersection here. All right. So my first solution is the intersection here. And that's going to be, let's see, over 1, 2, 3, 4, 5. And up 1, 2, 3, 4, 5, 6. And technically, I only care about the x. So yeah, so the x equals 5 is this first possible solution. We'll do a check in a minute. Now let's graph the red and the green lines. You guys might be able to use one of the grids that I gave you coming up next. Let me actually see. I've got those right here. Yep. Yeah, you can use. Yeah, I should have given you 2 grids. Yeah, you could use one of the grids that's on the bottom of that page, and you'll be just fine. Just fine. All right, so the green line, y equals x plus 1. Actually, oh, will I need a second grid? Y equals x plus 1 is the same as this one, right? So I guess like if I only have 3 lines I'm looking at, maybe you could get them all on the same grid. We'll try that. Clearly, Mr. Waddy is learning here as well at the same time. I wouldn't have necessarily broken these up like this, but that's okay. So let's see. So y equals negative 2x minus 4. It's close. Did I not opposite? Oh, this is plus 4. All right. Man, right? That was a plus sign. So up 4, right? 1, 2, 3, 4. And the slope is negative 2, so down 2 over 1. Yeah, you guys can get this all from one graph. I was thinking we were going to have 4 lines, and you guys might be working in only a single color. And I was just like, that would be really confusing. But yeah, one of the lines ended up staying the same. I should have thought of that. And so the intersection I'm interested in is not this one. I don't care about the red and the purple. I care about the red and the green, which was the same as the light blue. And that's right here. And so that's over 1 up 2. And the only number I care about from that is x equals 2, just the x. Nope. Wow. Good save, though. I spotted that. Yikes. Yikes. Nope, I'm only caring about the x coordinate for both of these. All right, so what we did, we broke these into 2 separate cases, one where it's equal to the positive and one where it's equal to the opposite. And then we wrote 4 separate equations. 2 of those ended up being the same. We found their intersections and we stole just their x coordinate. Now, let's just do a quick check. All right, let's check 5. So here's my check. Is the absolute value of 5 plus 1 equal to the absolute value of 2 times 5 minus 4? So let's see, 5 plus 1 is 6. 2 times 5 is 10. And absolute value of 6 is 6. Absolute value of 10 minus 4. Yeah, 6 equals 6. That works out. So x equals 5 is a solution. Let's try the other one. How are we doing for time? Yeah, we're going to get to classwork in just a minute. And let's plug 1 into the original equation. Is the absolute value of 1 plus 1 equal to the absolute value of 2 times 1 minus 4? 1 plus 1 is 2. 2 times 1 is 2 minus 4. And abs 2 is 2, right? It just leaves a positive number positive. And absolute value of 2 minus 4 is negative 2. Oh, but that absolute value swaps the sign, and it looks like I did find both solutions. Now, the way that technically, because you guys know how, well, we've seen it, maybe we don't remember it, how to graph absolute value equations. Let me look at the same problem. Oh, is it? Aha. Yeah, yeah, sometimes for some of these, you could. Now, because this is what I was going to do, and this was the mistake that I made when you first saw me, because I'm so thinking of it this way. I was going to write this as 2 separate absolute value equations. I was going to write this and this. And we technically know how to graph these, but I'm going to, actually, I still have my Desmos grapher up here, I thought. No? Do I? Here it is. All right, let's clear this. All right, let's graph both of those absolute value graphs. Y equals abs x plus 1. All right, so y equals abs x plus 1, close parentheses. Did that work? No, I don't think it did. Oh, it did. There it goes. All right, yeah, because it's a horizontal shift. So, right, absolute value graphs are a V for value, and that's what that first one would look like. And let's graph this one. Y equals abs 2x minus 4. Y equals abs, parentheses, 2x minus 4. Like so. And so here are my two graphs. Can I opposite invert colors here? Bing. All right. Shut off magnifier. And here we go. So if I graph these, which technically we have graphed before, absolute value. They're a little bit tricky. We did it through like transformations. But my two solutions, notice I do get two solutions here. Notice this point here, this point here. Notice this point is at 1, 2, and this point is at 5, 6. Notice that I would get the solution x equals 1 and x equals 5 from both of those. I would have gotten the same thing, all right, if I picked just the x coordinate of those solutions. So it is possible that I could have graphed both of these and found their intersection that way. But your book, instead of having you graph absolute value functions, they had you rewrite them as kind of get rid of the absolute value first, right? That's what the book has us do. But I just wanted to point out, technically, we could have done it a different way, and I think it's interesting that you get both solutions from a single graph. All right, well, thanks for watching, Internet friends. Have a great day.